So we're going to dive into another graph homework today. First one, they ask to give an example of a directed graph with two strongly connected components such that no addition of one edge can make the graph strongly connected. Okay, so a strongly connected component is any part of the graph where you can reach any vertex from any other vertex. So here's a simple example of a strongly connected component. Okay, so assume that this is our graph here. We've got just A and B is strongly connected. These two nodes are strongly connected because you can get to B from A and you can get to A from B. So if this was our graph, our whole graph right now is strongly connected, but if it had one more node, let's say C here, and let's say A can go to C, it's no longer, the whole graph is no longer strongly connected because C can't get to the rest of the graph, but the rest of the graph can get to C. So right now, this area right here would be a strongly connected component of our graph, and our whole graph is all three of these nodes. So they want us to give an example of a graph with two of these strongly connected components, and if you add any edge, then the graph is still not all strongly connected. So in this case, this wouldn't work, because if I add an edge from C to A, now the whole thing is strongly connected. And so, just so we've got everything here, let's add a D and an E, just like our A and B, and let's make these two strongly connected. So we've got another strongly connected component. Okay, so this is another strongly connected component here. And so now our graph has A through E, two strongly connected components, and if I add any edge, the whole thing is not strongly connected. And that makes sense. If there's no edge here that I can add that lets me get to everywhere in the graph right now. If I add an edge from C to the D and E, then let's try an imaginary edge here. So if I have our edge from D to E, now I can get from A to C to B. All these are I can get from these two to here to the C, and I can get from C all the way to these two. But if I'm in this side, I can't get out to this one. So I'm still, the whole graph is still not strongly connected, because if I start at A, I can get to every node. But if I start at E, I can't visit these. So that does not make the graph strongly connected. And is there any other edge that works? Well, I could add my backwards one from C to A. So now the whole C part is strongly connected with these two, but my D and E are still not connected. So there's lots of different examples you could make. I could even add another node. I could add an F down here. And I could, for funsies, I could connect this to here. And again, not strongly connected. And I could even add another edge here. So let's say this was our graph. Now we've got our big graph and all the nodes are actually connected. But there's no way I can add an edge that'll make this whole thing strongly connected. And you could kind of tell that because of the we've got two vertices with no outgoing edges. So that means once I get into the C node or the F node, I can't get out at the moment. So if I started at C, I can't visit any of the other ones. And if I started at F, I can't visit any of the other ones. And I can only since I can only place one edge, I can only fix one of these. So I can make F go somewhere, and that'll make F, connected with the rest. Or I can make C go somewhere, and that'll make C connected with the rest. But there's no way I can do both. And even if I connect F to C, C still can't go anywhere else, even though I fixed it for F. So, there's lots of different examples. So just go ahead and make two strongly connected components, throw in a couple random nodes, they can be connected or not, which is as long as they're officially in the graph. And that should handle that. All right, next one, they want you to find the strongly connected components for the graph in figure 1. So this graph right here, draw the metagraph where each vertex in the metagraph is a strongly connected component, or an SCC, of the graph. Okay, so there's a couple different approaches for this one. Usually I find the easiest method for this kind of thing is to start by looking for vertexes that don't have incoming edges. That's a good starting point to analyze. So I can see B and E have no incoming edges. And again, if you remember from before, if you don't have both incoming and outgoing edges, it's going to be very difficult for you to be a strongly connected component, because if you don't have incoming edges, nobody can get to you, so you can't be strongly connected. And if you don't have outgoing edges, then you can't get to anyone else, so you can't be strongly connected either. So you see how, like, most of these other nodes, they have a combination of the two, and that gives them the capability to be strongly connected. But since B and E have no incoming edges, they cannot possibly be part of strongly connected components, because you can't get into them. So what I would do here is I have my B and my E, and these are basically both going to be their own vertices, because they can't be part of the strongly connected components. And now I'll consider it with, I'll consider what our graph looks like without the addition of B and E. So without B and E, I've got our A, draw this out a bit real quick, to the C, to the D, down to F, down to J, this comes back up to C, and this guy goes down to H, goes across to G, down to I, back up to H. Okay, so having removed B and E, this is basically what our graph looks like now. And so now I just look at the next node that has that has both no incoming and no outgoing edges. And in this case, A doesn't have any incoming edges. So it's our next node that we look at, since we removed B and E. And so now I'll go ahead and I'll remove A. Whoa, crazy there. Now I'll remove A. And so with A removed, now we've got these nice little HGI and CDFJ. And so we're left now with just nodes that have both incoming and outgoing edges. And you can see here now that this very cleanly separated what was left into two strongly connected components. So, I'll rewrite this with a little more space. We've got our B, our E, and our A, and then our two strongly connected components. We've got our GHI component and our CDFJ components. And so yeah, so these will be all of the vertices in our new graph, our metagraph. And so now we just have to draw the edges for them. So let's see, our B edge, if we look here, it can go to A and G. So our B can go to A and it can go to G. Next, we've got our E. E can go to A and it can go to I. So it can go to A and it can go to our whole I node. And then next we've got A. What can A do? A can go to H, so it can go to this one, and it can also go to our C. And then finally, our GHI, so our GHI, where can that go? Okay, that can go to our other group, so This one can go here. And our CDFJ, can this one go anywhere? No, it cannot. So this is now our completed graph, and you could do it out like this, or you could try to put it back a little bit how it was. If we put it back how it was, just kind of estimating these spots, GHI and CDFJ. Oh, slightly amorphous vertex blobs here. And then, again, you could just draw it out how it was. And this one's probably a little bit easier to visualize. Although the other way to draw it is a bit more compact, but you can do either. Okay, I believe that handles all of our edges. Our GHI is 1. A has 2 outgoing, right? A also goes to here. Yep. So I can't forget this edge. Okay, there. I think that's got them. But yeah, so 2 possible ways to represent it, and that gives you your metagraph. Alright, next part. Describe a linear time algorithm which, given an undirected graph, undirected G, and an edge in it, determines whether G has a cycle containing that edge. Okay, so we've got an undirected graph. So make a simple undirected graph here. We'll do A to B. Let's put a cycle in it to C, D, and I'll be lazy. Okay, so this is our graph. We've got A, B, C, D. And so here we've got a cycle. B, C, D is a cycle. And they want a linear time algorithm. So linear time algorithm usually that's a hint that you're going to be using depth-first search or breadth-first search. Given an undirected G and an edge in it. Okay, so let's see. Well, if we removed A, then A doesn't remove an edge that's part of a cycle. But if we removed either this edge, or this edge, we would be removing an edge that's part of a cycle. And so you can think about what happens to the graph if this edge is removed. So we've got this edge from A to B. If we remove this edge and we go ahead and we start a breadth-first search or a depth-first search, we try to traverse this graph starting from A, we can't get to the rest of the graph anymore. We can no longer get to B. And so one could conclude that this is an integral edge to the graph to be able to visit. And if that's the case, that means it's not part of a cycle. It's the only path. If there's any other path to B, we would reach B. And so, so for example, let's say we got rid of this edge from B to C. If we got rid of this edge and we do a breadth-first search or a depth-first search starting from B, we can still get to the C node. That means that there's another route. There's another way to get to C. If there's 2 routes, then one of the routes ends up creating a cycle. So, using that logic, we can simply remove whatever edge it's talking about. So any edge from one node to another, we remove it, and we run a breadth-first search or depth-first search starting at the the outgoing node associated with that edge. So remember, most edges are considered having 2 vertices associated with them, the incoming vertex and the outgoing vertex. And usually the shorthand for that is U to V. And so in this case, we're considering the edge from B to C. That refers to this edge here we deleted. So if we have that edge, we remove it, and we see if we can still get from node B to node C. And if we can, then it was part of a cycle. So, this would be a linear time algorithm. Simply remove the edge that you're given in your graph and run a traversal of the graph starting at the first node for that edge. The edge that goes to the other one. Oh, I'm sorry, this should be out. And this should be in, because you go from one node to the other. But yeah, so just do that, and you should have a fairly straightforward algorithm for finding that. All right, next one, bonus. Scroll down so we have some space here. Give a linear time algorithm for the following task. All right, your input is a directed graph G, so we've got a graph. And the question, is G a DAG, a directed acyclic graph, contains a directed path that touches every vertex exactly once? So is G a DAG that contains a directed path that touches every vertex exactly once? You need to give an algorithm that proves, God, the grammar here, that meets the specifications. Answer yes if such a path exists. Okay, so we've got a directed acyclic graph. So let's try drawing one out. So you've got A to B to C to, I don't know, let's go down here to D. And yeah, so for now, this is a simple directed acyclic graph. We go A, B, C, D. And this one does have a path that touches every vertex exactly once. It's a pretty straightforward one. You go from A to B to C to D, and you've got it. Now, if I had another edge like here, from C to A, it's no longer a DAG. It's no longer acyclic because it has a cycle in it. So we don't have to consider that sort of thing. But, you know, say we had another node here, E, that C was also connected to. This is still a directed acyclic graph. There's no cycles. But there's no easy path that takes you to every node exactly once. Because if I go A, C, D, I missed out on E. I don't have this nice path. And if I go A, B, C, E, I can't get to D, and I don't have a nice path. But if there's another edge like this, then I do have a potential path. I could go A, B, C, E, D, and I can visit all vertexes exactly once. But if I went A, B, C, D, I would be messed up and I can't get to E, and that would not find the path. So the question is, if you have a graph that looks like this, where there does exist a directed path, but it's not a simple one that you can just, run down and follow, how can you find it? Is there an algorithm that does that? And so for this one, there's a couple of different approaches I can think of. The easiest one is probably to just do a topological ordering of the graph. So in this case, let's topologically order it. And so we do that with a depth-first search, and we calculate the post and pre-order. So we calculate the times where you visit the node and when you finish with the node. So the visit times and the finishing times, as the common nomenclature for that. So let's do that real quick. So for our depth-first search, we started A, we go to B, we go to C. We'll assume we go down the wrong path first. So we go down D, and D can't go anywhere, so it's done. 5 with post. We come back to C. C visits E. We've got a 6. Can't go anywhere. Post it at 7. Go back up to C. Post it at 8. Go back to B. Post it at 9. And we go back to A and post it at 10, and we're all done. So we've got our pre and our post orders. And now a strategy here would, we look at the highest post order. Our highest post order is 10. So we grab node A, and we basically remove it from the graph. So we remove A from the graph, and now we've got our B, C, D, E. Next we grab the node that has no incoming edges. So B is the only node here that has no incoming edges. So we grab B, and we remove it from the graph. Now we grab the next node that has no incoming edges. In this case, it is C. So we grab C, remove it. Now we look at the next edge that has no incoming edges. And D here has an incoming edge because it has this edge from E to D. Here, just so you can see this edge is gone and this edge is gone. So now our graph, the only one with no incoming edges, is E. So we grab E next. And then all of what we're left is with D. So here we've got a nice little topological ordering, A, B, C, E, D. And we're able to see here that if we followed this path, A, B, C, E, D, we would find that nice little directed path that visits all the vertices. So our algorithm, our first step would be to run a depth first search to get our ordering. Then we go through it and we simply check for nodes that don't have any incoming vertices. So we go part by part. No incoming vertices after removing source vertex. And then after we do that, and we've got our list of nodes, we simply check if we visited all of the vertices. Check if it contains all vertices. And so this should work in linear time because it simply runs a depth first search and then goes through and checks. So it essentially does 3 linear time operations. And you can do any number of linear time operations and still be a linear time algorithm as long as that the number of those is a constant number. So if I'm always doing 3 of these operations, no matter how big our graph is, then it's still a linear algorithm. All right, so that should handle it. That should give us a nice algorithm for that. Let me know if you have any questions here. And again, you can see here when we did our depth first search, gave us these nice finishing times, and we can see that the finishing times in descending order will give us this resulting topological order. It's a little easier to visualize it as just looking for nodes that have no incoming edges, but you can also do it by simply going down descending finishing times. But either approach is fine, and let me know if you have any questions. Hopefully this cleared it up, and I'll see you next time. Have a good day.